Hello sir, myself Priyanka. Today I'll be presenting our framework for benchmarking bias mitigation algorithms in representation learning. This work addresses a critical gap in machine learning research. Let me start by highlighting why this research is crucial. In recent years, we have seen numerous cases where machine learning systems unintentionally produced biased predictions. Consider the commonly cited example of loan approval systems or hiring algorithms showing systematic bias against certain demographic groups. Our research addresses three key problems: the lack of standardized ways to compare different fairness methods, the difficulty in measuring the effectiveness of bias mitigation techniques, the need for a common framework to analyze these approaches. Our framework utilizes two carefully selected datasets. First, the CA-MNIST dataset, a modified version of the standard MNIST dataset, where we have deliberately introduced controlled correlations between features and eligibility criteria. As you can see in figure 3, this allows us to systematically test how different models handle bias. Second, the adult set, which provides real world demographic data. This dataset helps validate our findings in practical scenarios. We have implemented several state of the art models. The LAFTR family of models, which includes LAFTR DP for demographic parity, LAFTR equi-op for equal opportunity, LAFTR equi-odd for equalized odds. As you can see in the balanced case, these models show different trade-offs between fairness and accuracy. Coming to the results analysis, let's examine our key findings. In the balanced case, we observe that all models perform comparably. However, when we reduce the privileged group representation, we see significant performance degradation. In the adult dataset, the story becomes more complex. Notice how the LFTR variants show better adaptation to real-world scenarios. Coming to the metric deep dive, looking at the table 1, let me explain how our fairness metrics demographic parity shown by the formula measures the absolute difference in prediction rates between protected and unprotected groups. A perfect score of 1 indicates complete parity. Equality of opportunity comes into two variants. For positive class, ensuring equal true positive rates; for negative class, ensuring equal false positive rates. Our experiment revealed several crucial insights. First, model performance degrades predictably with increased correlation between sensitive attributes and target variables. Second, in the real-world scenarios, we observe more complex interactions between fairness metrics as shown in the adult dataset results. The trade-off between fairness and accuracy is not linear. However, notice how small improvements in fairness can sometimes lead to significant accuracy drops. These findings have important practical implications. When implementing fair ML systems, start with simple metrics like demographic parity progress to more nuanced measures like equality of opportunity as you understand your use case. Always monitor multiple fairness criteria simultaneously. And finally, coming to the conclusion, to conclude, our framework provides a standardized way to evaluate fairness approaches, clear insights into the trade-offs involved, practical guidelines for implementing for
The
ML
story so
systems.
far
Thank
has
you.
been, let's start with what we learned from the papers. The paper showed us, the first paper that we studied, showed us everyone was initially using information for fairness, but Emma had some serious practical issues. This is about the fairness and how AIs have been unfair. So they proposed a distance correlation as an alternative to cover this. The benchmarking paper showed we needed standardized ways to test fairness. Different models have different strengths. Real world performance varied significantly. What we did about it, our framework contribution. We took these insights and built something practical. Data analysis, dataset analysis. We worked with CT Minset, a controlled testing ground, adult dataset, our real world providing ground. Model implementation, we tested multiple approaches, LAFTR variants, CAFAR, and FFEAE, basic MLPs, and CNNs. Key findings from our test. On CI Minset, balanced case, this is a balanced case that we're talking about. All models perform similarly in the ideal situations, confirm theoretical expectations. But when it comes to the challenging cases, like ideal data set, models struggle differently with biases. Some handle correlation better than others. On adult data set, real world complexity, models showed more variable performance, trade-offs became more pronounced. The cool part, what we learned was practical insights. For developers, start simple with demographic parity, monitor multiple fairness metrics, be ready to adjust based on real data. For researchers, keep trade-offs. Either you want to choose fairness or accuracy. Either we want to choose simplicity or robustness. Either we want to go theoretical or practical. What actually worked? Simpler approaches often provided better. Monitoring multiple metrics was crucial. Real-world testing revealed hidden challenges. Why this matters? Let's talk about for industry. Clear path to implementation for AI, which is very needed at this point. Better understanding of trade-offs, more reliable testing methods. And for research purposes, standardized comparison framework, reproducibility results, and clear directions for improvement. What are the next steps for this project? So immediate plans are being extend testing for more data sets. There's always an option. Develop new fairness metrics, improve computational efficiency. When it comes to for the long-term goals, industry-specific guidelines are something we want to focus on, and automated fairness monitoring is also something is an interesting area for the fairness domain, and better handling of multiple protected attributes. So the bottom line of this project was what we have built here connects theory to practice. We took the theoretical insights about distance covariance and MI from the paper that we read and turned them into a practical testing tools. Our framework shows how different approaches actually perform, where they struggle and excel, what works best in real world scenarios. Uh, whether you want whether you're building loan approval systems or hiring algorithms, you now have a clear way to test and improve fairness. That's it. Thank you, sir.